and lengths in polar coordinates. So a quick review of our sector right here. We know that from trig, the area of our sector is 1/2 radius squared times theta, and theta must be measured in radians. So we're going to consider the region bounded by r equals f of theta, our curve, where f is continuous and non-negative on our interval from a less than or equal to theta less than or equal to b, and our two rays theta equals a and theta equals b, a and b, b being the bigger theta, a being the smaller. To find the area, partition our closed interval AB into n equal subintervals, then approximate by taking the sum of the area of those n sectors formed. So for each sector, the change in our area sub I equals 1/2 f of theta sub I, all that squared times change in theta. So we're looking at that particular section right there. Well, just like we've done in the past, we build all these up, we turn them into a summation, but this is an approximation. And to get our approximation to become an actual value, we take the limit of this summation as n goes to infinity of our summation, and we have either one of these two formulas. We're going to integrate from a to b 1/2 of f of theta squared d theta, or in general, integrate from a to b 1/2 r squared d theta. Again, whatever our function will be in terms of theta, we'll put that in there. All right, example time. Find the area enclosed by one loop of the curve r equals 4 sine 3 theta. All right, so here's my curve. Went to my calculator, drew it out, so put it on my polar graph. We're looking for finding the area of just one petal. Now the question is we need to find out, when does our r equal 4 sine theta hit the pole, the origin, if you will, every time? So we'll set this equal to 0 and find out all the times when we're going to come around and cross and go through the origin or the pole. So divide over the 4. Sine of theta equals 0 at 0 radians, pi radians, 2 pi radians, 3 pi radians. So 3 theta equals 0. 3 theta equals pi. So to find theta, we divide over the 3. And so we're looking for just one petal. So from 0 to pi over 3, that's when we create our first petal. Pi over 3 to 2 pi over 3 would be down here. 2 pi over 3 to pi would be right there. All right. So there's my lower bound, there's my upper bound. Let's go put this into our formula for finding the area, our integration formula. We'll substitute in our 4 sine of 3 theta. We're going to square that, and we'll integrate it from 0 to pi over 3. All right, so let's square this. We're going to get 16 sine squared 3 theta d theta. We can probably take the 16, factor that out front, call it 8 times, so 16 times a half is 8. And we have the sine squared theta, which is not going to be helpful to us. So we're going to have to remember one of our identities here. So sine squared theta, there's one of these for cosine squared theta, so we're going to have to look these up to make sure we have them all. And we're going to replace sine squared theta with 1/2 times 1 minus cosine 2 theta. And so that 3 gets multiplied to the 2 theta, so we're going to have a 6 theta in here. Again, with the 1/2 being multiplied to that binomial, we can take the 1/2, factor that out to the front, and multiply it to the 8, so we'll make that a 4. Now this is easier for us to integrate. So 1 becomes theta, minus cosine 6 theta will become 1/6 sine of 6 theta. Remember, you'd have to do a u substitution, let u equal 6 theta, then take the derivative of both sides. You get 1/6 d theta. And then to solve that, you got to factor that over for du when we make the substitution. So that's where the 1/6 is coming from. And so now we're going to evaluate this. Well, the first thing I notice is that we got a 0 down here. So sine of 6, 0. That's still going to be 0. 0 there, so we don't have to put in the 0. That's all going to cancel out. So we just have to plug in the 4/3 and see where that's going to get us. So looking at the inside of my trig function, 6 times pi over 3, that's going to be 2 pi. So again, this will give me a 0 times my 1/6. So it looks like we're going to have just 4 pi over 3 square units. That's just for one petal. If we wanted to find the area of all 3 petals, then we just multiply our answer by 3, and it would be 4 pi square units. All right, so again, look up your sine squared theta here and your cosine squared theta. I believe the cosine is 1 plus cosine 2 theta in there. So remember that. We're going to need it here. All right, example 2. Find the area of the region that lies inside the first curve, r equals 3 cosine theta, that's the one in red, and outside the second curve, r equals 1 plus cosine theta. Where do they intersect is where we're going to want to integrate from. So again, there's my 1 plus cosine theta, there's my 3 cosine theta. When we set up our integration here, our r that we're going to be squaring is going to be the right function minus the left function. And remember, we square the functions first, then subtract, not subtract and then square. All right, so again, to find our a and b, we're going to set these two equal to each other to see where they intersect. So we'll subtract over the cosine theta, makes it 2 cosine theta equals 1. Divide over the 2 is a half. All right, so take the inverse cosine of a half. That's going to be 60 degrees, or pi over 3, and 5 pi over 3. That's down in quadrant 4. However, if we said pi over 3 to 5 pi over 3, that would be going outside over here. So we're going to change our 5 pi over 3 to negative pi over 3. So we'll integrate from here, this segment, all the way through to this segment. Okay, so now you can see where our thetas are at, and we have one smooth continuous. So we don't want to go from out here because there's no area represented out there between the two curves that we're looking for. If it would be this small area right in here, and that's not what we're looking for. We're looking for this one. All right, so I set up my integral from negative pi over 3 to pi over 3 of 1/2 times right function, 3 cosine theta squared, minus left, 1 plus cosine theta squared, d theta. Now, before we go any further, do you notice that below the x-axis and above the x-axis, they're symmetrical about the x-axis? I can flip it and be the same. So we're going to change this negative pi over 3 to 0, but then double, because we're only going to find half the area, so we need to double it. That way, that 2 and this 1/2, we can cancel that out. Excuse me. All right, so let's square these. So 9 cosine squared theta minus, FOIL this one out, then distribute the minus sign, minus 1 minus 2 cosine theta minus cosine squared theta d theta. Combine like terms, we get 8 cosine squared theta minus 1 minus 2 cosine theta. Okay, here we go, cosine squared theta. There's that identity I told you about. We'll have to know this one too. So cosine squared theta is 1/2 times 1 plus cosine 2 theta. So multiplying that by 8 makes that 4 plus 4 cosine 2 theta. So I'm going to swap this out. And then subtract this 2 cosine theta. Oh, not like terms, hold on. We'll add the 4 and the negative 1. So we'll make that a 3. So now we can integrate this. So I need some more room. So 3 will get integrated to 3 theta. 4 cosine 2 theta will be 4 times sine 2 theta times 1/2. Again, think of that u sub when integrating is like the derivative in reverse. Instead of multiplying by the derivative of the inside, you are dividing by the derivative of the inside. Then minus 2 cosine theta, integrate cosine theta is sine theta. And we'll integrate this from 0 to pi over 3. So we substitute in our pi over 3's in all our spots. So 3 times pi over 3 gives me pi. I get 2 pi over 3, so that's, like saying 120 degrees. That's radical 3 over 2 times 2, which will be just radical 3. And this is still radical 3 over 2. Cancel the 2, so we'll have pi, looks like plus a radical 3. Oh, they're going to both cancel out. We get pi square units. The 0 was not needed because sine of 0 is 0. Sine of 2 times 0 is 0, and 3 times 0, so that canceled everything out. So here's the area between those two curves. Next is our arc length. The length of the curve with polar equation r equals f of theta between a less than or equal to theta less than or equal to b is going to be our integral from a to b, the square root of r squared plus the derivative of r squared d theta. We talked about this before for our arc length. We're just going to apply it into our polar equations. So if we had to find the length of a polar curve from 0 to 2 pi, inclusively, for r equals 2 minus 2 cosine theta, well, we'll just plug this into the formula. We have our r. We're going to square it. We're going to find our dr d theta here. So the derivative of 2 is 0. We don't need it. The derivative of cosine theta is negative sine theta times our negative 2 out front. It's going to make that 2 sine theta. So we can plug that into our formula. We're going to have to FOIL this out. So that's 4 minus 8 cosine theta plus 4 cosine squared theta. Multiply this out, 4 sine squared theta. Wait a minute. Sine squared plus cosine squared. That's a 1. So these two terms right here, we factor away the 4. That becomes 4 times cosine theta plus sine squared theta, which is just going to give us 4. So we can add that 4 to this 4, and that gives us 8 minus 8 cosine theta inside of our radical. So right here, I want to factor out the 8's. So square root of 8's out in front. And the reason I want to do this is because the square root of 1 minus cosine theta is familiar to me. That's part of my half angle identity. So in my half angle identity, I have the square root of 1 minus cosine theta over 2. So all I need to do is get this to substitute over here. So we manipulate this, we square both sides, we get sine squared theta over 2, multiply over the 2, 2 sine squared, and we have our theta over 2 equals 1 minus cosine theta. So I can put this 2 sine squared theta over 2 in for 1 minus cosine theta. And now we'll factor out the square root of 2 with the square root of 8. And that will become the square root of 16, which will become a 4. And what's left on the inside is the square root of sine squared. Well, that'll cancel out to be just sine of theta over 2. And then there's your 4. And now we can integrate this, and it's a lot easier to do. So if we integrate sine, that's going to be negative cosine. And then, again, remember here's a 2. That because you do your u sub, take the derivative of the inside, would be 1/2. So if you divide by 1/2, that's like multiplying by 2. So that gives me negative 8 cosine of 2 pi over 2 minus cosine of 0 over 2. Well, let's see. Cosine of 0 is 1. This will become cosine of pi, which is negative 1. So negative 8 times negative 1, oh wait, negative 1 minus 1 is going to be negative 2, so that's going to give me a positive 16 units long. Notice it's not squared because we're looking for a linear distance here, not an area. All right, that ends 10.4. We'll come back to 10.5 in just a bit.